Hi, everybody. Welcome to week 3 of your adventures in Orgoland. I thought I'd start with our new theme song for Orgoland. Here it comes.
Sunny day, sweeping the clouds away. On my way to where the air is sweet. Can you tell me how to get
To Orgoland, how to get to Orgoland, how to get to Orgoland. Okay, I'm getting desperate. No, it's only week 3, which means I've only added one more chain of lights, a little more bling, and a little more fun as we continue to play in Orgoland in 3D. Okay, so let's go play in chapter 7 a little bit, and that's why this video is sponsored today, or brought to you today, by chapter 7.1 and 7.4. Hopefully you recognize that little theme music. It's from one of my kids' favorite shows. All right, today we're going to look at these two models, and hopefully from last lecture you were able to build these with your model kit. So if you haven't done so, please try to even create some type of tetrahedral carbon with 4 different colors attached to it. And what I'm curious about is, which model did you build? Which one of these two do you have? Do you have the one, and if again, this is going to be a little tricky, if you were holding it and the red chloride and the green methyl were in the plane of your view, you're looking down this bond, is the H sticking out at you, like mine, sticking out, and the blue is going back into the paper? So did you make this, or did you make this one? And you might be thinking like, wait, they're the same. They got all 4 colors. But as you can see, we're venturing into a space and time and place where we are going to create such a thing as mirror images of these molecules, and that these 2 molecules do not superimpose on each other. Let's try it. If I were to take this one on the right and try to rotate it to keep, let's say, the red and green atoms colors the same. So I rotated mine and tried to match. As you can see, my reds and greens match on these molecules very fine. But then what I want you to notice is that the blue and whites do not. These 2 are what are called non-superimposable molecules. They are called enantiomers of one another. Welcome to Orgoland language. Yes, more language. And they have what are known as chiral centers on them. Okay, and so this is what we're going to look at in chapter 7 a little bit, is these unique, very unique kinds of molecules, but they are very unique just like us, because we are chiral. Our hands are chiral. Please, always, well, I'm going to come back to this hand reference all the time, in that you can see the hand is a mirror image of the other one. Like if this hand was looking at a mirror, it would see this one, okay? So they would see each other. But when I go to superimpose them, meaning lay them flat, both pointed down, so the top of my hands are both up, and now try to put them on top of each other, whoa, I have chiral hands, which means my entire body is chiral. And therefore, a lot of compounds and drugs that we play with, as you'll see in a second, actually capitalize on this idea of being chiral and having a very specific right-handedness or left-handedness. Okay, so this is going to be very cool. The molecule we are looking at right now is 2-chlorobutane. We would say that this molecule is chiral, and that these 2 structures are enantiomers of each other because they are non-superimposable mirror images. Okay, let's get more specific. Little stereocenter is what we would call there. And as we're going to see, when you have a little stereocenter, you want to put a little asterisk at that carbon to warn the reader and the person looking at that molecule, whoa, you have a stereocenter, you have a chiral atom in your molecule. All right, so why should we care? Even though I just gave you the big lead in that drugs and everything about our bodies is chiral, let me show you some heavy duty ideas. Some of you might be familiar with thalidomide. It was a very popular drug that was given to pregnant women in the 1950s. And because it was very effective at removing any nauseous feelings that pregnant women were having. So it was a nice anti-nausea drug. But in the 50s, what they didn't know is that its enantiomer, which came along for the ride in the drug because it's so similar, it looks exactly like the anti-nausea form of it. That mixture was given to women, and the teratogen is what's known as something that causes severe birth defects. And so women had very, very awful birth defects for their babies based on this drug, thalidomide. So they finally pulled it off the market and realized that not every chiral molecule, not every enantiomer of one another behaves the same in our body. And so let me show you a few other examples of this, where one enantiomer, say the plus enantiomer and the minus enantiomer, we're going to see that coming up very soon. Where you ask? Yes! Lab 3. We're going to play with this idea of enantiomers, positive and negative. And what I want you to notice is some drugs, even like naproxen, have one enantiomer that is a pain reliever and great for a sore back, but the other enantiomer is known to be toxic to the liver. So drug companies now have to purify and separate these two enantiomers from one another. Not an easy thing, but they need to do that because we do not want to take something that's toxic. Again, on the fun side though, there are other enantiomers out there known like carvone, and carvone is very cool in that one enantiomer of carvone smells like caraway seeds and the other one smells like spearmint. So our nose has chiral receptors in it that bind to one enantiomer or another of the same molecule almost and cause completely different neurological effects on our brain. So chirality is a fascinating idea, especially since these molecules seem to look so similar, right? So to have a chiral center, let's try to make sure we're clear about this. Notice when I held up 2-chlorobutane, the most important thing about my chiral center is that it has 4 different groups attached to it. Not 4 different atoms. I could have the same atoms originally attached to that carbon, but as you go away from those 4 atoms, if they become different anywhere down the path of those 4 bonds to that tetrahedral carbon, anywhere down that path, that will make that carbon chiral. Okay? And any molecule with one chiral center is considered a chiral molecule. You will see in a minute we will have chiral centers, but not chiral molecules. Whoa, how is that called? Well, when it's not chiral, as you can see from the name here, more nomenclature, we will call it achiral. Okay? So let's go play. Let's see if we can spy chiral carbons, chiral centers. So take a second here, and if you want, I have a little small print here. Sometimes trying to determine the carbon NMR and the number of different carbons that show up in a molecule will help you recognize symmetry, or help you recognize when 2 carbons are identical or even 2 paths are identical. And whenever 2 paths coming off a carbon are the same, you do not have 4 different groups. It is achiral. Take a second here, pause. Let's see what you come up with these 3 molecules. Okay, you ready? Let's see if you came up with the same thing I did. I saw that there was a chiral center in this molecule. And I do mark it with an asterisk just to help you spy it, as opposed to just saying, oh yeah, there's a chiral atom in there. Do you see it? How about this one? No. The two ethyl groups coming off that molecule are identical, so no chiral carbon there. But as soon as I make one side of the ethyl group different than the other ethyl by putting a double bond, I have created 4 different groups around that carbon, and therefore it is now chiral and should have 2 enantiomers, 1 plus, 1 minus. Okay, cool. So let's be very careful. How do you spy an achiral molecule, even if it might have chiral centers? What is that all about? So let's show you what that's all about. Try to find a plane of symmetry. And this could go through bonds or atoms. So for example here, if you have a plane of symmetry in your molecule, the molecule is achiral. So notice this one is fairly straightforward because you'd be looking at that single carbon, right? And instead of 4 different colors, there'd be 2 white atoms, 2 hydrogens pointing out at you in this one. And therefore, if they're both hydrogens, then you could not tell them apart. And therefore, if you can't tell them apart, this molecule is achiral. So it has a little plane of symmetry. Notice the plane of symmetry is going down and through the atoms, and that methyl group is spinning around with 3 H's coming off of it, even though it's written sideways. That really is a very symmetric plane of symmetry through there. So keep an eye out for this plane of symmetry, or keep an eye out for when there are not 4 different groups attached to your carbon. How about this one? Notice that I do have 2 chiral carbons here and here, because the paths going off of them are all completely different, and there is a wedge hydrogen in there as well. But since this molecule can't rotate or move at all, it's stuck in a cyclohexane ring, our favorite, you cannot move these methyls at all, and therefore the 2 methyls are mirror images of each other. So even though you have 2 chiral molecules, 2 chiral centers, excuse me, the whole molecule has a plane of symmetry and looking at each other, and therefore the whole molecule is achiral. So you can have chiral centers, chiral molecules, you can have chiral centers, and achiral molecules. Whoa! Okay, so this is a lot of visualization. I hope feel free to build these and play with them to see what's going on. Okay, so let's see if you can spy the chiral or achiral molecule and the chiral and achiral centers. So go ahead and put asterisks by a chiral center, but don't assume that just because you have a chiral center, you have a chiral molecule. So try this, pause. Welcome back, welcome back, welcome back. Okay, so let's go through this one, and I think, let's see if you got the first one right on the left here. Chiral, yes. Did I put an asterisk there? I don't think I did. Oh no, let's go back and put an asterisk. I need an asterisk. That is my chiral center. And so notice now wedges and dotted lines are really, really important, okay? To show the 3-dimensional shape and help me see the 4 different groups coming off of it. Here, it might look like there's a plane of symmetry originally, like it looks like a ring and an OH and an H that are actually coming out at you and away, and you might be able to chop them right in half, but you cannot because of the alkene. Chiral center and chiral molecule. How about this one? All right, this is the exciting one. So drum roll, please. we got here? We do have two chiral centers. And it looks like there is no plane of symmetry until I love sound effects. Okay, until you take this molecule that I have right now for you that is in this conformation on the left, okay? Notice it is zigzag. Here is the OH that is pointing up, or excuse me, hold on. Let's get it just right. Here is the methyl, excuse me, that is pointing down. Here is the zigzag to the methyl pointing up. And here is one OH sticking out at you. Here is the other H hiding way back here, going away from you. Okay? So how did this become a plane of symmetry? How did it become the drawing on the right? What I did is I just took this CH3, and since it's a single bond, single bonds can rotate. So I took this CH3 and I rotate it down to make it a mirror image with the other CH3. And as soon as I made these CH3s mirror images of each other, see what happened to the OHs and the Hs? That is so cool. The OHs and the Hs also became mirror images of each other. So these two are chiral centers, but the whole molecule has a plane of symmetry based on the fact that I can rotate single bonds. And therefore, we need to get either very good with our visualizations or just keep in mind single bonds can rotate around that middle single bond and rewrite the structures so that you can see if you have a mirror image in the plane of symmetry in the middle of your molecule. Okay? Pretty cool. All right. Take this problem. Which molecules are chiral? And as always, please label the chiral centers. So you can have chiral centers and achiral molecules. So this is looking at not whether you have a chiral carbon, but whether you have a chiral molecule. Okay? So let's bring this one to class. Please have an answer, cut and paste your answer and put it right into the Jamboard. Okay? Cool. Let's keep playing with these. Now, the reason we want to play with these now is because if I have enantiomers, then I need to call one 2-chlorobutane something different than the other 2-chlorobutane. They both can't be called 2-chlorobutane. Similar to why one alkene can't, all alkenes can't be called the same, because some might be E and some might be Z. So we have E and Z alkenes. What are we going to do with these guys? How are we going to make sure that I want you to build this one or this one? I have to be able to tell you something. And look at it again. Here comes some rules to help us identify how to tell these apart. And again, these three dead chemists come popping up everywhere, where we're going to use the highest atomic numbers as you move out from the chiral center to start naming them. Okay? So, and we're going to need to prioritize them. So take this molecule, which, let's make sure we're all playing with the same one. I have two. Wait, do I know? No, that's this one. Right. So I'm going to play right now. Notice this blue one is pointing out at you. Just like on the screen, I have wedge coming out of the paper. So this is the red chloride, then blue CH2, CH3, then, wait, green. Where'd my green go? Oh, green CH3. Pointing back, sorry, going away from you. It's over here. Yes. And the white hydrogen, oops, wait, no. Oh, I want it kind of coming at me. Oh, did I have the right one? Okay, so notice it's not easy. So I want to make sure I have the correct one for you. So it looks like I have the correct one. Ugh. Again, video is tough because mirror images of the actual camera. So I'm trying to make sure I have the right one for the camera. Okay, it's definitely not that one. So it's this one. Whew. Okay, so I want to have my red atom and my white hydrogen in the plane of what I'm looking at, down the plane. And I want to have the, can't believe this is, here we go. Okay, and I want to have the blue atom pointing out away. I guess I have to hold it. No? Oh, this is gonna be frustrating. Okay. Let's see which one I got. Okay, I hope you have the right one. So we're gonna build these. And what we wanna do is start prioritizing them. Oops, sorry. Let's prioritize them based on the 4 groups and the 3 dead chemist rules. So what I see here is a chloride. This is definitely the highest priority out of all 4 groups hanging off. And the lowest one is the hydrogen. It is the smallest little atomic number I have. So I can prioritize 1 and 4. Then it's a little different. I have 2 carbons that are tied, but then look at the 3 bonds attached, right? And this has 3 hydrogens, and this has a carbon and 2 hydrogens. So now I've prioritized my 4 groups, and I can move to rule 2. View the molecule with the 4th priority pointing away from you, and try to keep these 2 in the plane, okay? So that when you're looking at it, you have the 4th priority pointing away from you, okay? And the red and the green and the blue, this is what I see. Let me make sure I got this right. Yep. So this is what I see, what you see. We're having this white one pointing away from us. Way out here is the white atom. And then as you zoom in, here is the 3 other atoms and their priorities of 1, 2, 3. Okay? Now we're ready to name this specific enantiomer. Ready? Here we go. If we take this one, which has 1, 2, 3, with the 4th priority pointing away from you as you look at this screen, what you want to do is start to turn this wheel or rotate this molecule by holding on to this carbon and either rotating it so that it always goes from 1 to 2 to 3. So I always want to rotate 1 to 2 to 3. If I do that, then that's rotating this molecule in the old-fashioned, who knows if anybody has these clocks anymore, but think of it this way, you're also rotating it to the right. So I'm rotating it to the right. So beautifully enough, if I rotate it to the left, it's counterclockwise, but right in Latin for right is rectus, so we will call this R, okay? So this specific enantiomer that I'm holding in my hand, that you're holding in your hand, to go from 1 to 2 to 3, I have to spin it to the right, holding that 4th bond away from me. And as I look at it, I'm spinning it 1, 2, 3, therefore it is rectus, it is right. If I have the other one, it would have to have been spun to the left. Hold up the other enantiomer and prove me right or wrong. So this one is definitely going to be R, the one that I have on the screen. And for the chemical name now, just like alkenes where you put E and Z out in the front, here for this molecule, you're going to want to name it the R 2-chlorobutane as opposed to the S-2-chlorobutane. So we will now use R and S to help us identify which enantiomer you want the person to build for you and play with, so that you don't take the wrong enantiomer as a drug or smell, and that would be very bad. Okay? Let's play with this one. Take a look at this molecule. Hopefully you can spy that, yes, it is chiral. And so please bring the chemical name and your answer to this. Take a screenshot of this, whatever it takes, post it in the Jamboard, bring your answers, and let's see how all your new study group partners, brand new study group partners, feel about whether this is R or S, and what do they think about nomenclature and how they would actually name this compound. One thing to let you know here, in the cyclohexene, that cyclohexene can never be anything other than what it looks like, which is 2 little hydrogens on the same side, and all the bulk high priorities always here. So even though it's a Z alkene, alkenes in a cyclohexene will always be Z, so you don't need to actually put the designation in there. You just need to tell me that you have a cyclohexene. It's always going to be Z. All right, so come up with a name for this. Keep practicing your R and S, pointing the 4th lowest priority away for you, and keep practicing. Practice, practice, practice. After you bring this one, tons more. Can't get enough. So bring this one to class. What's your answer for this? Please justify it by prioritizing and putting your numbers 1, 2, 3, and 4 on the chiral carbons. And then, as you can see, I have them all oriented slightly differently. So feel free to use your models to try to create these to begin with. But at some point, we are going to need to not use models, like put the model away and try to visualize R and S in our own mind. And to do that, there is a couple things you can do. You can make a tetrahedral carbon with your 2 fingers, wedge and dotted line coming out at you, going away from you, see? And then in the plane of the paper. So you can kind of create a tetrahedral carbon this way. I've seen students create 3, the ones that are pointing out at you like this, and rotate this way or that way, this way or that way. So grab it and make the 3 bonds, where the 4th bond is the back of your hand, going away from me. 3 this way, that way. So at some point, and feel free to talk to the tutors, they also have little tips and tricks on how to visualize a tetrahedral carbon with only your hands and no models. That would be awesome. So try to figure out a way to do that as well. Bring it to class. Last but not least, you can't get enough practice with R and S, and it's strictly visualizations. So I've given you several more molecules, some for each whiteboard. Please feel free to play with all of these, even though your own group will have its own specific set of questions. Okay, and I will put these in all the Jamboards. So come to class with answers. Try not to come to class to figuring it out. Try. Venture out, give an answer, be humble. Your new study group members will appreciate your humbleness and your willingness to put yourself out there and give an answer. All right. I hope you have a great weekend, and I hope you're diving into chapter 7 already, because I can't wait to start playing with our lab kits and play with chiral molecules in our next lab. Okay? Have a great time. Please send me any questions you have. I love questions, and I'll see you soon.